time to continue. It's time to go to New York. It's time to go to PLX. Thank you, Michelle, for joining us today. What can we do for you? What can you do for us? The floor and the attention of everyone is yours.
Sure. Thank you so much for introducing me. I'm going to start sharing my screen 1 second here. Okay, great. Can you guys see me?
Crystal clear.
All right, great. So, hello, I'm Michelle Hyers, the Director of Engineering from PLX, and today I'm going to be talking to you about transforming optical structure technology through innovative system integration. So basically what we do here at PLX, so hello from New York, is manipulate light. So this is really relevant to this talk today regarding laser beam and pulse shaping. So anything that involves manipulation of light, such as sub-arc sunken beam delivery, targeting, bore sighting, beam steering, folding, laser systems, interferometry. So we have some of the examples here. So we're really the pioneers in retroreflector technology. So if you can see in the bottom left here, that's kind of where our history had started in making these retroreflector systems. And that was just kind of the intro into this series of different applications. So we have all these other systems, lateral transfer hollow retroreflectors. We have this example here and the periscope example. But really the heart of what we do, a lot of this custom OEM application and integration. So really a solutions provider. So I thought this talk would be great today to really integrate some of these applications in beam and pulse shaping into the platform of what we do. So in terms of just getting to know and understanding what we do at PLX, we are working at all these different levels here, from the assembly levels, making these optical assemblies, all the way up to subsystem and system integration. So that's really the power of our technology, to really go through all these levels. And the idea is always to kind of get to that integration level, is where we can kind of produce the most benefit for your systems. And then what, I'm going to mention this a little bit more later, but what we're really looking for in terms of Epic is really working with key partners in this area. So really finding interesting applications and coming up with solutions for the market together, utilizing a lot of our expertise and what we are already doing, and really pushing what we can do. So in-house, we really work on engineering design. We have our team of engineers, and we go through a whole process to really come up with and design optical assemblies that perform extremely well. Really what we're best known for in our expertise is making these systems that work in really robust conditions in terms of vibration, shock, thermal systems. So we do an FEA analysis. We do a lot of environmental testing to really prove out those systems. And then, we also are doing that fabrication, precision assembly, all the testing, in-house coding. And that gives us the ability to really control what we can do and really push the boundaries of that as well. So in regards to this talk today, there's a lot of different methods and implementations for beam and pulse shaping. So what I wanted to kind of talk to you guys, one of the things that we really work on in our main technology, I'm going to talk about and introduce shortly, is monolithic optical structures, which we call the M.O.S.T. So there's all these different elements. You guys, some of the talks already went over a little bit, is different ways to basically manipulate the beam or pulses. And a lot of those can involve many different methods and elements that can be integrated into a monolithic structure. So if you take something like a system, one portion of this may be a beam shaping or pulse shaping unit, but there's also ability to really think about this at a higher level in terms of integration, where that element could be, or that system could be part of a larger system. And that is the benefit of a monolithic structure. We can put all of those elements into one highly accurate assembly. And so you can really think about these optical structures and systems on a different level, where you might not have to have all these different separate portions, but you can really kind of have an all-in-one solution. And these monolithic structures are really beneficial in terms of thermal capabilities, vibration environments. So it's not really limited to some of the conventional optical system approaches. So with that, if you think about a monolithic style approach, so this kind of all-in-one structure, you can really get high accuracy. So PLX specifically, we can go down to sub-arc second beam deviation, and that's the overall assembly level beam deviation. And we also are very strong in what we call invariant optics. So I mentioned the retroreflector example as an example. But really expanding on that, you can also carry those into the monolithic optics as well. And it's highly configurable. So anything that, any kind of systems that you can think of, we can really combine at the assembly level. So there's really not a limitation. That's just the technology is really just the structure and the ability to put these things into the assembly, but there's no limitation of what you can put together. And the stability is really, again, a lot of our systems, we call them are just happen to be in a lot of the military defense markets. So these battlefield ready. So things that if you're transferring that over to a lab or a scientific approach, any vibrations and laser power and all these issues you might think of are really performing well in the most extreme environments. So it's usually not a concern. It's actually a high stability system. Component integration. So we're talking about all those different elements. And I think you guys went over some of those. These you might have in those systems, you might for beam impulse shaping, you might have reflector, like mirror elements. You might have lenses, you might have diffractive elements. You could have filters, polarizers, all these different sorts of different methods to get to an overall optical system. And in that, you end up with a very complete enclosed design. You don't have to worry about alignment issues and stability. Things aren't going to be moving and changing for those elements. And in terms of, you still might have some optics or elements that might need to move or modulate. And when you get into things like that, another thing I wanted to bring up is that our ability for PLX to really integrate with MEMS. So some of these systems in this application could be MEMS driven. And so we have actually done and collaborated with partners in this field to really provide, these are examples of basically other MEMS mirrors and using like our retroreflector technology, but integrating in a deformable actuated system. And this is an example that we worked on for actually this free space optics to provide optical communication. So this is just, I want to just show this as another example. Scale for us is also very flexible in terms of going down to even this MEMS level up to even very large systems. So really PLX, we're really focusing, especially this past year, really pushing the limits on what we can do in innovation and building up our technology. So I had mentioned this before. So this is our M.O.S.T. This is our monolithic optical structure technology. And I'm going to show you guys just a quick video, but I just want to show here, this is an example here. This larger picture is an interferometry product that basically we offer. But if you look at all the photos below, they're all different configurations using the same technology, but the applications are vastly different. And so there's a lot of flexibility in that and what we can do. So we're really looking for those very interesting, exciting applications, and we're really looking forward to working and collaborating with you guys. So let me show you guys a short video. You guys hear that okay? with the M.O.S.T that was just interested in the video is really going over the ability to take all these different elements, and specifically for this application, whatever elements you need, if it's diffractive elements, if it's a series of different multiple filters or anything you can really you can put into the system and really build it into your overall optical system. So there's no really limit of what we can do in terms of the type or number of elements we can put in here. And you really get this compact, we call this like the sandwich-like structure. It gives you this this plug and play sort of ability to take your optical system and really put this one element in to replace multiple different systems. So with this, you get the optical stability that we talked about and the shock and vibration resistance. You get this extremely high accuracy. You don't have to worry about all these different elements and components getting loose or moving around in different conditions. So you get this kind of permanent alignment that's very powerful. And in terms of what we can do all different types of materials. These just happen to be some of the examples shown. Let's say we're fused silica or low expansion glasses, but we can do metals, ceramics, and we have before. And a lot of this is just depending on the CTE. All these systems are athermally designed, so we try to match CTE. But this allows us to have really strong accuracy even over a large thermal excursion. So with PLX, we really take all of these capabilities. So, the heart of what we started out historically is just doing these hollow retroreflectors. That's one of our core components here, and our monolithic structures is really built onto that. We also do a lot in lightweight optics. So whether it's the optical and mechanical or both systems really optimized for these specific applications. And then invariant optics, that's also another powerful technology of what we do. And all those come down to, again, the system integration. So we really like to get in early into your guys' applications because we really can have such an advantage for you at just the initial level, assembly level, but also this integration level. So just to give you an idea, these are some of the sizes and metrics of what we've done before, but we're always pushing these boundaries. This is just a guideline, a starting point. So beam deviations on an overall system down to 0.2 arc seconds. In terms of sizing, I mentioned the opto-MEMS. In retroreflectors, we can go down to 2 millimeters. It's just a standard size that we offer, so we can push down if we need something customized. And just some of the scale of things, on the large side of things going up to, meter level is not an issue as well. So we're really not limited in size. In environmental conditions, this is where we really shine in terms of providing the best performance, keeping that performance in adverse environments. So whether it be shock, vibration, temperature, these are kind of just, again, guidelines of what we can do and we've produced before. So in terms of applications, we have, a lot of experience in multiple markets, defense, aerospace, and commercial, and we've done some of these applications in terms of laser beam and pulse shaping in these industries. And we're looking to kind of expand on what we can do and who we can partner with. So we have these examples on the left-hand side of some of them, and I'll show you some more kind of examples to see what we can do. So this is just the image really showing all the different applications and variations of what I just talked about. So you can really expand on some of these. Some of these on here are the monolithic structures. Some are the retroreflectors. On the bottom, you can see a retroreflector array that looks like that honeycomb structure. We have ones that are basically rotary devices. We have pentaprisms, pentamirrors. We have autocollimators. There's really just such a vast amount of solutions. So we are really providing, you guys have your application, you give us the details. So you give us the details of what you want to achieve and we can design, fabricate and test and come up with the high precision assembly that really meets your needs. So it doesn't matter if there's very tight, high precision, vibration, shock, all of those is exactly what we are the best and excel at. So that is PLX.